All right, campers, welcome to MediaComp9. Since you're not watching the baseball playoffs anymore, because, well, the Cardinals are out of it, so who cares? It's time to do MediaComp9. So let's begin. Let's talk about rotating pictures, shall we? I want to talk about rotating them either 90 degrees to the left or 90 degrees to the right. So let's start with left. What has to happen is there's a couple of things to notice. That the pixels will end up in a different place in the target. In fact, what happens is the column values become row values. And so the target X will become the source Y. But then, because they have to rotate around, the target Y will become the source with -1 minus the source X. So in this case, 1, the target X will stay 0. It'll stay in the same column. But the target Y will be the width, the original width, which is 3, minus 1, which is 2, minus the source X, which is 0, so we end up at 2, 0, right down here, or 0, 2, right here. And you can see how that rotates through for all of them. So we're taking this thing and rotating it that way. Okay. The algorithm for this looks like that. It looks just like what I just described. You loop through the source X, you loop through the source Y, you grab the source pixel, you grab the target pixel, and you set the values for using the X and Y coordinates, and then you copy the color from the source pixel to the target pixel. Piece of cake. We should be very familiar with these. Right rotation goes the other way, but the other important thing is, once again, column values become row values, but this time the Y's and the X's are reversed so that the target Y will become the source X, and the target X will become the height -1 minus the source Y, because we're going to take this guy and rotate it around that way so that the 4 and 1 will be at the top and the 3 and 6 will be at the bottom. So just imagine you have a pivot right here, and you're going to bring this around and rotate it like that. Piece of cake. So let's do it, shall we? We'll go over here, and I've got this program that this is using the new standard where we create an instance of ourselves so that we can keep all of our methods as regular instance methods and not static methods. I'm going to comment this out, and we'll try doing a rotate right here. And so we'll compile, get back over here, and we'll do the main and Dropbox, media sources, and we'll do the beach. And we'll turn the beach around to the right. Thunk. And so what we get, remember, the left-hand side becomes the top. The right-hand side becomes the bottom. And you notice how we correctly made the picture the right size. So, okay. Now, the other cool thing to notice, though, is if I did this twice, then I'd have turned the picture upside down. So we can try that. So let's do that. What I'm going to do here is I'll rotate the picture again. Now this rotate right method returns me a picture, so I have to create a new picture. And then I'm going to show you that picture at the end. And so we'll do that. And we'll try this again. Dropbox. Media sources, and we'll do the same picture. There's the beach, and 2, 1, rotated and rotated. So here's rotation twice, here's rotation once. So rotating once, we get it up on its side, rotate it twice, and it's upside down. So that's pretty cool. So you can use a rotate twice. You could do it, of course, 3 times. But the third time, of course, would be the equivalent of the rotate left. So let's do the rotate left here. We'll hide these. And we'll rotate left. And we don't need bar anymore. And we'll compile. And rotate left works exactly the same way, except we're going to tilt it the other way. And beach 2. And 2, 1, thunk. And now with a rotate left, the left side becomes the bottom and the right side becomes the top. But otherwise, the pictures are pretty much identical. So, well, not pretty much, exactly identical. So, all right. So moving along then, from rotation we move to scaling, where we want to make the picture bigger or smaller. Now we're not going to scale an infinite amount here. We're just going to do a couple of simple examples of scaling. So for scaling, you can make the picture smaller. And one way to do that is to increment the source x and y coordinates by a number larger than 1, which implies that you don't use all the source pixels in the target. So to make a picture smaller, you basically throw out some of the source pixels, and that will reduce the size of the target. To make the picture bigger, you do the other way. You copy the same source x and y pixel to more than one target x and y. So you use the source pixels more than once in the target to scale it up. So scaling down, the opposite of scaling up, we're going to create a picture which is 1/2 the size in each dimension, so that will be 1/4 the size. Now, one way to do this is to just average the colors. So we take these 4 colors and average them. We take these 4 colors and average them. We take these 4 and then these 4. And those averages become the colors in the 4 pixels here that are different. We're not actually going to program that. I'll leave that as an exercise for the interested reader. The version we're going to, the version we're going to use is this one, where we just use every other pixel. So if we do this in both dimensions, we'll get a picture that's 1/4 the size of the original. By using every other pixel in each dimension, we'll use half the pixels in each dimension. And so if I started with 640 by 480, I'd end up with 640 by 2 and 480 by 2. I'd end up with a 320 by 240 picture, which is 1/4 the size. So the scaling down algorithm is like this. You create your target source objects. You loop with the source starting at 0 and the target x starting at 0. And then as long as you're less than the source width, that's actually less than the source width minus 1, because you have to be careful when you make these smaller. We'll increment the source by 2, and we'll increment the target by 1. Same thing with the y, in the y direction. So, okay, how about scaling up? In scaling up, we're going to do the opposite. We're going to scale up by a factor of 2 in each dimension so that the new picture will be 4 times the size of the old picture. Scaling up, we're going to do it in a sense exactly the opposite. We will take each picture and we will double it in each dimension, each pixel, and double it in each dimension. So 2A's, 2A's in both places. 2B's and 2B's, 2C's and 2C's, 2 and 2, 2 and 2, 2 and 2. So the resulting picture will be twice as big in both dimensions. All right. So just to give you a little bit of a break, here's another example of, this time not so bad, computer science on TV.
What if we were to enlarge This part of the photo, not the face, just this part of the window.
Are you thinking of the reflection?
I'm wondering if maybe we can see the kidnapper's face in that side view mirror.
It's worth a shot.
I need a CSU photo tech up here now.
Yes, I'll continue to hold.
Detective, enhanced and enlarged.
Thank you.
The enhancement only increased the pixelation on all these. You can't even see there's a side view mirror.
It's not like on 24, Castle. In the real world, zoom and enhance can only get us so far.
But you can't even, there's no reflection, it's just mush.
There's no reflection, it's just mush. Not like in 24, not like in CSI. All right, moving along. Oops. The scaling up algorithm, there's like 3 or 4 different ways to scale up. One way that I will show you, we actually take the source X and target X and source Y and target Y loop control variables and make them doubles instead of ints. And then we increment the source X and Y by 0.5. And then when we grab the pixels and reset them, we cast that double back into an int. That will truncate the values, so the effect it will have is that we will use each source pixel twice. Because 1 will become 1.5, but when you cast it to an int, it'll be back to 1. And then the next time it'll be 2, and that'll be fine. But then it'll be 2.5. When you cast it, it'll become 2 again. So we're going to do both just by 0.5. So let's take a look at that. I'm going to quit rotating, and I'm going to scale down first. And so let's take a look at the scale down picture. The scale down is actually very simple. We have the target X and the source X and target X and source Y and target Y loop control variables. We go through the source X and source Y dimensions, and every time we do, we increment the source X by 2 and we increment the source Y by 2, but they only increment the target X and Y by 1. That will squeeze us into the new space. We need the -1 so that we can take care of odd-sized pictures. And then the copying is just exactly what you've seen before in terms of copying. We go grab the source pixel, grab the target pixel, and then set the target pixel color to the source pixel color, and we're done. So let's see how this works. Go here, media sources. Let's take my wife at Versailles. 1, 2, 3, pow! And there she is, in front of the gates to the palace, and 1/4 the size of the original. So that looks pretty good. And notice that the picture looks actually maybe even better. All right, so scaling down seems to work. Let's look at scaling up. We're going to use this. We're going to use the trick of doing going up by 0.5. Okay, so here I make my source X and target X doubles, and I make my source Y and target Y doubles, and then I increment the source X and the source Y by 0.5, so I'm going to get fractional parts. But then when I go and get them, I need ints, and so I cast it back into an int. These will get truncated every other time down to the previous value, and these will be okay because I'm incremented by 1 every time. Otherwise, it's exactly the same. And so let's see if that works. I have to go back up to main. Oh, wait a minute, sorry. Which one's, sorry for the confusion here. Which one is this? This is scale up 1, okay. And we're coming back to the main here. We'll go there. And where's scale up 1? Scale up 1 isn't here. Well, we'll just have to fix that, won't we? Picture foo equals rpic dot scale up 1 picked. All right. Let's compile that. Golly, I hope this works. And we'll click here, and we'll go to the Dropbox, back to media sources, and we'll take this picture of Barbara. I think this should work. Oh, that's a small one. Oh, that's be a good one to make bigger. There you go. And we make her bigger. So she starts out being really tiny, and we make her 4 times bigger. This is actually Barbara Erickson, one of the people from Georgia Tech who did all of this stuff. And notice you can see that this is really 4 times the size. And copying the pixels does a pretty good job of reinforcing it. All right, sports fans, so that is pretty much everything I have to say today. We are done. Have a good time. Take care.